I was interested in the subword one too, and I was like, oh, I want to read this one. Then I okay. You still might not.
Okay, so it is 7:30. We can get started. So this chapter that we've started, we're going to be focusing on full cycle. And we're focusing on the simplified version first of this full cycle data path. And again, we're only covering a subset of the instructions. I've covered the entirety of the instructions. The data path would just be a little bit complicated for the introduction. And we talked about the data path a little bit last time. More specifically, we talked about what are the elements that we need, what's the difference between the combinational elements and the sequential elements, and then what is the ordering of those elements in the data path. And in this lecture, we're going to finish the single cycle data path and connect everything together. And just as a reminder that these are the subset of instructions that we are going to implement. So we have R types, I types, and J types. And they're 32 bits long, and they have these different formats. Okay? So opcode is always in the same place. RS and RT, they exist, are always in the same place. And then this is where we cover more differences. We have RD, shift amounts, font code for R types, the immediate for I types, and then this longer chart address for J. And we'll know from the opcode immediately what type of field. Are we an R type, I type, or J? Alright. So we already talked about from last time, the very first thing that we have to do is fetch the instruction, right? So let's just build out the data path part for fetching instruction first. So we have this one of instruction memory. So this is our field in memory that is only going to contain our instructions. What else do we need for instruction?
Something to decode the instructions.
Instruction fetch on. I just want to get the instruction. Okay. And so we need program counter. There's one more component that we'll need.
Need to increment the program counter.
So we have program counter, and then we have this adder to increment program. Because if we didn't, then we wouldn't be able to go to the next instruction. So here are our three components. So we have instruction memory, program counter, and the adder. And here's how we're going to connect them. So we have program counter first, right? It's the first thing that we're going to need to access. Because without this, we don't know where in memory to read. So the program counter is going to point into the read address of the instruction memory, and we'll get out the 32-bit instruction from that address. And then at the same time, program counter will go into the first input of this adder, and the other input of the adder is 4, right? Because we are word aligned, and we have byte addressable memory. So we increment by 4 to get to the next word, which is the next instruction. And that is going to be saved into program counter. And again, this is just a simplified view. We cannot do any branching yet. With this data path, only increment PC by 4, right? We'll add the branching, jumping later on when we get there. So is there any question on this part? Okay. So the next part is for R formats instructions. So R types. We need to read 2 registers and then perform the arithmetic and logical operation and then write the register result. Okay. So we need the register file in order to read those registers. And we also need to make sure that our register file has these different inputs and outputs. We have two registers to read from. So that's gonna be RS-RT. And this is where our output comes from the register file, the read data. So this is the 32 bits from the register. And then we have the write register, which would be RD in this case. And then the write data, which is the result from the ALU. Okay. And then we have this reg write control signal. And then we have the ALU. So we talked a lot about the ALUs previously. And we covered some subset of our small subset on how we would make an ALU to do that. And now we have this ALU that is going to cover the entirety of the subset. But we know how it would look underlying. So we have our two operands and the results. So now we need to connect these as well. So here is our example. So if we had the instruction that we get from instruction fetch, we can grab the different fields. This would be RS, this would be RT, this would be RD, right? And then the read data, RS and RT would be the inputs into the ALU. And then we would also have the funct code and the opcode to tell us what is the ALU control signal that needs to come here to perform whatever it is. Is it going to be the add? Is it going to be a subtract? Things like that. So we're missing some other combinational block that would calculate this control signal. We'll cover that another time. And then the output of the ALU goes into write data. We're just getting these things from the instruction. And so T2 is RT, T3 RS, T4 RT. This is the data from RS, data from RT, and then when it goes through the adder, it's the data from RS plus the data going into the write data. So this is the data we want to write, and the write address is for load and store instructions. We again need to read register operands, right? This RS is our base address. And then RT is going to be our destination. Or if it's a store word, it's going to be the register data that we need to write to memory. And then we also need to calculate this 16 bits offset with the base address. So we're again going to use the register files, but we also now need to access memory, and our ALU needs to be able to not just use RS and RT, but now RS plus this immediate. So here are the units that we're adding. We have the data memory. We have controls to say, are we going to write, enable? Are we going to read? And then we have the address of where we're going to write or read. And then if we're going to write, we need to give it data. And then if we did read, what is the data that we're getting at? And then we also have this sign extension unit. Because in order for us to do the calculation of the offsets, we need to make sure that's bit fits. So all this does is, if it's a negative coming in, it just appends ones. If it's a positive coming in, it appends zeros. Right? So here is going to be our example. So we have load word. This is RT. This is T2. And this is RF, our base address. And again, we would get all this data from the instruction. So RS is 11. I'm going to get the base address out here. And then down here, I have the 4, which is again just from the instruction. And I'm going to sign extend the 4 by pre-appending 16 zeros. And that's going to go into the ALU. So we have RS 4. This is our address. I was pointing to the address. And we're a load word, so we don't have write data, right? We're just going to get the read data out, which is memory at that address, and write it to register T2. Right, so this is a separate data path using the same components, but like we mentioned already, we're sharing the ALU, we're sharing the register file with the R type instructions. We need to have a way in order to select what are the inputs that are needed for the instruction. Before we cover all those different components that we're going to add, we need to support branching, right? And branching, we're going to read register operands and compare them, right? And then we also, after the comparison, might need to change PC. So in order to compare the operands, we already made this in the ALU, right? We can just use the ALU. We subtract them and check the zero confidence. So if we were checking that for a branch on equal, then we check that the zero flag is 1. For checking for a branch not equal, we check that the zero flag is 0. And then after that, we need to calculate the target address and then update PC if we need to. So here is our data path. So we have, again, the instruction, and we're going to get RS and RT from the instruction. And we also get the sign extended immediate from the instruction. And then with the sign extended immediates, we're going to shift it left by 2, right? Because our bottom 2 bits are always 0 because our instructions are word aligned. So we save 2 bits in the instruction field by doing this shifting afterwards. And then we have PC plus 4 from the previous data path for the instruction fetch, right? Because we're always adding 4. And we add those together to get the branch target. And then we have RS, RT, ALU operation from opcode. It knows it's going to be branch on equal or branch on not equal. And then the 0 flag is what we're going to use to determine if we're updating PC or not to this value. So here is the combined data path in order to do loads or stores, as well as R types, because remember, we're sharing the ALU, and they don't use the same second operand. Right? So R types use RT, which would be selecting 0 here. Whereas loads and stores use the sign extended immediate, which is selecting 1 here. So this is how we can share the ALU. Okay. And then the other thing that we're sharing is the register file. The write data for R type comes from where?
In memory.
For R type.
Oh, for our type.
RG, the destination.
What's the write data?
The output of the ALU.
Yes, the output of the, right? Right here. And then what's the write data for loaders? Oh, yeah, just the load, because store doesn't have write data.
Memory.
Yeah, put them there. So we're again sharing this write data port as well as the write register, right? So the mux to share the write data port is shown here. And it has the control signal mem to reg. So if we are an R type, mem to reg needs to be 0. If we are a load word, mem to reg needs to be a 1. And that's how we're sharing the write data. And then what's not shown yet is we're also sharing the write register port, right? Because RD is the write register for R types. But the write register for load word is
Unextended.
RT. Or us. RT.
or load word, write register. Not
RT.
RT, right? So we also need a mux here to decide, are we writing to RD or RT, right? But if we ever need to share these resources, we just need these muxes, right? Just to be able to select between what is the proper inputs for the current instruction. So if we put all of these things together, right, we started with the instruction fetch. Then we have this is what we would call instruction decode, because we're getting the registers, getting all the operands, things like that. This is the execute phase, where we're doing the actual adding operation. This is memory, right? So if we need to store to memory, or if we're loading from memory. And then coming back over here, this is write back. So this part. Coming back to the register file. And this is just all of those data paths that we just covered connected together, but we don't have branching added yet. So now this is adding the branching logic. So we have the shifter for the sign extended immediates. And then we have the adder. And then from the 0 flag, we'll figure out, should the PC source be just PC plus 4, which is this input? Or is it PC plus 4 plus the sign extended immediate, right? And that would update PC. So again, we're sharing PC, the register. We need to have a mux. Is it going to be PC plus 4, or is it going to be the branch target address? So are we good with this data path so far?
There's still a mux that needed to be added.
Yeah.
From the register.
Yeah, we don't have it yet. So now this is the final single cycle data path that we're covering, minus we don't have jump yet, right? So we can do R formats, we can do I formats. So R types and I types, we can do the entirety of those subsets with this data path. And then here is your MUT sharing the write register port. So now to show. Okay. But in terms of the other parts, we are seeing how do we figure out these control signals. We'll cover that in the next lecture. And the inputs into that are going to be the opcode, right? As well as the funct code for our types. So we'll cover what exactly this is doing and how to make this in the next lecture. But these other fields, they are not changing, right? The bits of the instruction 25 to 21, that is always RS if there's RS, right? 20 to 16, this is always RT if there is RT. 15 to 11, this is RD. 15 to 0, my sign extended immediate. Well, my immediate, that is going to be sign extended, right? And then 5 through 0, this is funct code, right? Like I mentioned, we're going to use that to figure out what the ALU needs to do. So these different paths are correct from the instruction. All we're missing is how do we know which format type it is to figure out these control signals? And then if it's R type, how do we know what ALU operation to do here? So this is your poll for your code is 242. And then the blue lines are highlighted, mean that that's the path that the instruction is taking. So if it's just the black lines, the instruction is not using that path. So the question is, based on the highlighted data path, what is the instruction type? Is it R type, load word, store word, or branch? So answer this on your own first. Any The answer is coming into the full. Let's. We are close to the threshold, but not quite there. So do talk to the people around you. Again, the blue lines are the highlighted data path.
What are we thinking? So. Right from the view go, I saw that the instruction lines. Think be that instructions didn't overlap the big RD, and that's going to the muck, therefore immediately I can tell it's a different type of Then as we go through to double check it, instruction 5.0 goes to the ALU control, which is the pump code, which is used in the R types. And it goes up, and I'm looking at that ALU, and the ALU result not going to memory, going straight through the bucks back to right data. So we did an R type operation on it. Looking up, seeing the PC adder. Notice the only thing that goes through all the way is adding PC by 4, so increments, and there's no branching or anything going with the memory as well. So nothing's written to memory or taken from memory. And so it's some sort of R type. Based on going through that, this is what I saw from the network.
I do resubmit your answer if you were to change. And we are well past. So going over this together. Okay, so we're always starting at PC, right? We need to fetch the instruction first. So we get the instruction from the instruction memory. PC is incremented by 4. And we'll follow the rest of this pathway. So after we have the instruction and we read the opcode, this is what's being highlighted. We have RS being used, RT is being used, and then we also have RD being used. Okay, because here it's highlighted, and from the MUX to the right register, we're highlighting the RD part, not the RT part. Okay. So already I know what the answer is, right? There's only one instruction type that uses RD.
Okay.
That's R type, right? But we can finish looking through this because there are other ways to know as well. So the rest of the instruction, and then we're branching off down here for the last 6 bits of the instruction. This is
Code.
Func code. So again, that tells me this is R type, okay? And then out here, after the register file, this is RS, this is RT, okay? Because we knew that from these. And we're selecting RT. So this doesn't, RS and RT here doesn't immediately tell me this is R type, but it does exclude load word store, right? And the result gives memory, right? We take the results and we're writing that back. So this again tells me R type, okay? Because if it was load word, store word, load word would just stop here. I mean, store word would stop here. Load word would get the data from the memory and write that back. And the other thing that tells us that it's not the other I type of branching is we're not using the shifted left sign extended. We're taking PC plus 4 and we're incrementing by that. All right, so here's the next one. data path has changed a little bit in terms of what's highlighted. What is the instruction type? So again, do this on your own first. I don't see any more answers changing. We are past the threshold, so there's no need for a peer discussion here. Alright, so PC is just +4, right? And then here, I'm using RS. I'm not using RT as read. I'm using RT as write. So this, just from this, it tells me what the instruction is, right? Not just I type, but I'm writing. It's going to be load word. Because we can even eliminate store word because store word doesn't write to the register. Store word would actually read from R2, right? Just to confirm, coming down here, we're getting the sign extended immediate as one of my operands, base address as the other, adding, which gives me the address in memory, getting the read data, writing that back to RT. And then again, PC is just PC plus. So for now, this tells me load word, but we do have other I types that we will cover as well. And that would be the I types of add I, sub I, but for now we haven't covered those. So that's why this RT write register tells us load order for now. So this is the load order. And next one. So again, do this on your own. answers changing anymore. And we are gonna pass the threshold. Read from PC. PC plus 4. RSRT. And then we're also using the sign extended immediate. So because we're using the sign extended immediate, we know it's I type. Now the key is, where is this sign extended immediate going? It's not going into the ALU. It's going into the shifted left by 2 and this adder for PC plus 4 plus the sign extended immediate. So that means it's not load word or store word. This is a branch. Okay? And then the ALU, the 0 flag, tells us if our branch is happening or not. This is the last one. Again, answer on your own. Again, that's the threshold. I don't see any answers changing. So PC plus 4, RS, RT, sign extended immediate tells me it's an I type. So it can be load word, store word, or branch. But the key here is RT is going into write data for memory. So this eliminates branching, because for a branch, RT would go into the ALU. And it also eliminates load word, because if it was load word, RT is the destination. We don't even read from the second register code for load word. So this is store word, right? So store word is C. Okay. So that is all for today. You do have reading. And the other thing is homework 2 is due before class, right?
Yes. It's like,